Hi everyone, welcome to the Wednesday night Chem Help ASAP live stream. So it looks like we've got good connection tonight. I'll look at the chat, OG benchmarks, if you will let me know, make sure my audio is coming through. Okay, audio is good. These are always our concerns, right? Okay, so I had some requests for some acid-base work. So we're going to kind of start at the beginning of acids and bases. We're going to talk about definitions. We're going to do some calculations of like pH and pOH and other things like that. And we're going to work through a neutralization, or sometimes called a titration problem. We'll look at different points along the titration curve. And depending on how much time we have, we'll also talk about weak acids and bases. So at this point, I'm just going to see how much I can get through, see how many questions there are. And I will probably do some type of acid-base work next week as well. But you guys let me know what you want to see, if you want to continue on, if you want to repeat some of the stuff that we've done this week, just, let me know, whatever you guys need. Okay, so with that being said, and everything looks good, let's go ahead and start with our first page. This is not a problem. This is just definitions. Okay, so the most narrow set of definitions for acids and bases comes from our Arrhenius definitions. Now, these were the first stab at putting a definition on what an acid and a base was. So we've got an acid, which is something that produces protons, or H plus, in aqueous solution. And a base is something that produces hydroxide ions, or OH, in aqueous solutions. And just so you know, for certainly all of this live stream, we are only going to be working in aqueous solutions. Okay. So let's do an example of this. So for an Arrhenius acid, let's use the most common acid. That would be hydrochloric acid, HCl. It gives you H plus and Cl in an aqueous solution. Another way to write this, and really maybe a more accurate way to write this, is to write hydrochloric acid. It is in an aqueous solution. It's in water. And so it forms the hydronium ion and the chloride anion. These two equations, in terms of doing your math for your problems, these are going to be equivalent. So, and I don't think we have anything for this live stream that's going to be different. So for this live stream, we can assume that H plus, let's say the concentration of H plus, is equal to the concentration of H3O plus. So we're going to consider these two species equivalent. The reason why I tend to quibble with H plus, although it does make things simpler and easier, which is fine, is H plus does not exist in aqueous solutions. That proton will always attach itself to a water molecule, or to something else if you've got something else in solution. But in terms of hydrochloric acid in aqueous solutions, it's always going to be attached to a water. So this is the more accurate equation if you're talking about being accurate chemically. Okay, so that's an acid. It produces protons, or hydronium ion, in aqueous solution. Let's do an example of a base. So a base is something that's going to produce hydroxide ions. So one of the most common bases is sodium hydroxide. And when you put that in water, you get sodium ions and hydroxide ions. Now, in this case, hydroxide is fine, just hanging out. It does hang out with the water, but we don't have the situation like the hydronium ion and H plus. Okay, so that is an acid. That is a base, according to Arrhenius. These are good definitions. We still use these definitions. It's totally fine. But we ran into a problem when we considered ammonia. Now, ammonia is NH3. And the chemists knew that it was a base. It had basic properties. But obviously, you don't even have an oxygen. So how are you going to produce hydroxide? So this is a base that doesn't produce hydroxide. So we need to expand our definition. And hence we have the Bronsted-Lowry definition of acids and bases. Now, you'll notice that acids pretty much stayed the same, except instead of saying produce, we now say they donate protons in aqueous solution. But again, we're focused on this H plus species. So this is still totally valid for a Bronsted-Lowry acid. For a base now, instead of focusing on the hydroxide, we're going to say that a base accepts protons in aqueous solution. And I'll show you what I mean by this. So we're going to take ammonia, which was the problematic molecule for chemists working with the Arrhenius definitions. They're like, it's a base, but it doesn't produce hydroxide. But I'll show you what it does. So if you put it in aqueous solutions, you get an equilibrium. And what happens, oops, I forgot my N, is you get NH4, or the ammonium cation, and you get hydroxide anion. So what has happened here? Well, you've had one of the hydrogens, or one of the protons from water. It's coming over here. It's being accepted by that nitrogen. And so instead of having NH3, we now have NH4. And of course, instead of having H2O, we now drop back to hydroxide. Okay, so this is the Bronsted-Lowry definitions are an expansion on the Arrhenius definitions. Sodium hydroxide is still a base. If we think about sodium hydroxide, and this does sometimes cause confusion, because if you go up here to sodium hydroxide, you're like, where do we accept the proton? I'm not seeing any proton accepting here. Well, what really happens is it's the hydroxide itself that is the base. So sodium is what we call a spectator ion, meaning it just hangs out. It doesn't do anything. But what happens is, and maybe I'll write this over here, is you have your hydroxide in water, and it is going to accept a proton from this water. So you're going to, okay, I know this looks confusing, but what happens is you take one of these protons, it is accepted by that hydroxide, so this hydroxide now forms water. And then, of course, this water, now that it has one less proton, becomes hydroxide. But this is what is going on. This is why it is a base in both the Arrhenius and the Bronsted-Lowry, because it is donating hydroxide, and it's the hydroxide that accepts the proton that makes it a base in the Bronsted-Lowry. And obviously, like if you had an acid in solution with the hydroxide, then it would take the proton from the acid. But at this point, like for the definitions, I'm just working with an acid in aqueous solution or a base in aqueous solution. We will do the neutralizations in just a little while. Okay, so with these definitions, and again, we're working in aqueous solutions, I do want to make sure that we go over quickly our equations for calculating things like the concentration of hydronium, the concentration of hydroxide, your pH, and your POH. Now, I'm not going to necessarily go into the pH scale right now. Again, if that's something you want to see, just let me know. We can certainly talk about that. But these are our equations that we're going to use to do our calculations. Now, these equations come from the autoionization of water. But the main thing is to know how to use these equations. So remember, pH and POH, these are not only logarithmic scales, but they're inverse logarithmic scales. So they scale with concentration, either concentration of hydronium for pH or concentration of hydroxide for POH. These two equations also come from the autoionization of water, which again, I'm not going to get into, but I can if that's something that you guys want to see. But really, I feel like this is the one that really helps me the most, is to be able to switch between pH and POH. You're just going to, you can either add them together to get 14, but usually what you do is like you have pH and you want POH, you're going to take 14 minus pH, and that'll give you POH. So these are really useful equations, as we will see in just a few minutes, for not only calculating things like pH, but also switching between like POH and pH as well. Okay. Let's make sure there are no questions. There are no questions. I know that was really, really quick rundown of the definitions of what an acid and base are, and the equations. And there's really a whole lot more there that we can get into. Again, just let me know if you want to dig into the nitty gritty of that. But let's go ahead and start some calculations. All right. So hopefully this looks familiar if you've done some acid base work in your classes. So if 35 grams of hydrobromic acid, HBr, is added to 975 milliliters of solution. What is the pH of the solution? Okay, so we're aiming to get to pH here, which means at some point, probably at the end of the problem, I'm going to be using this equation right here. So just so we identify which equation we want to use. But we have a molecule, a chemical in aqueous solution. Let's see what's going on with this. So let's write a chemical equation. So we have hydrobromic acid, or HBr. It's just hanging out in water. And we're going to get hydronium, and we're going to get the bromide anion. Again, another way to write this, if this makes more sense to you, you can absolutely go like this, where we go with more the Arrhenius definitions, where we're producing H plus in solution. These are equivalent in terms of how we are going to do the math. All right, so let's go back again to our pH equals negative log of our hydronium concentration. So hopefully you remember that concentration, or in this case molarity, so we're measuring concentration in molarity, is equal to our moles of solute over liters of solution. So that is how we measure concentration. If we want concentration, we need both of these variables, or, you know, if you have concentration in moles, you can calculate liters, et cetera, et cetera. So we've got 3 different values, and we just need 2 of them, and we can solve for the third. Well, what I am seeing here is that if I want to calculate concentration, I'm going to need moles. All right, so I'm going to need moles of my acid, which is HBr, but I've got grams. So for me, my first step is to convert grams into moles. Oh, okay, so we had a question. What are some indicators in a question we use to figure out which equation we're using? Okay, so that's a great question. Like, how do you know which equation to use? Well, for me, for this question, because it said pH, I immediately went to this top equation. I'm like, okay, pH, at some point I'm going to use this. Now, I might have to use some of these at some point. And again, we'll see problems where we're going to have to use more than one of these equations. Actually, I think it's the very next problem that we're going to do. We're going to have to do that. But that's how I first identify what I want is pH. Bam, I'm going to want to use this at some point. Maybe I don't know when. And that's where I start. I guess for me, I kind of work backwards a little bit. I say, all right, I'm going to use this equation. I'm going to need concentration of either H plus or hydronium, however you want to think about it. What is concentration? How do I calculate that? Okay, well, I calculate that here, which means I need, if I'm going to calculate concentration, I'm going to need my moles of solute and my liters of solution. Well, I know for sure I've got grams. So let's just go ahead and get that into moles, because at some point I'm going to need moles, and grams is just not very helpful. And this is another thing that I think can help students. If you're looking at a problem, you're totally stuck, you're like, I have no idea what to do. If you have grams, go ahead and convert to moles, because probably you're going to have to convert that to moles at some point in the equation, and that can at least be a first step to kind of get your brain going. But yeah, that's always the challenge with these, is where do you start? How do you think about this? And everybody kind of has their own unique path. This is how I identify it. So I hope that answered your question. Okay, so where was I? Oh yes, I'm converting grams into moles. So I have 35 grams, of hydrobromic acid. And let's go ahead and get that into moles. So that's 80.991. This is just the molar mass. I already have it written out for myself, so I don't have to calculate it. Okay, so notice, of course, that my grams of hydrobromic acid cancel, and I'm left with moles of hydrobromic acid. Okay, so this is all well and good, and this, oops, let me switch back to blue. This equals 0.4325 moles of HBr. Okay, great. Can I plug this moles of HBr into here for my moles of solute? Well, I could, but remember, I want the concentration of hydronium. So let's make this concentration of hydronium, let's go really specific. I need moles of hydronium over liters of solution. Okay, so this is what I specifically need. This is the concentration I specifically need and the moles I specifically need. Okay, well, moles of hydronium are not the same as moles of HBr. That is not the same molecule. But we can connect these two, and we can connect these two with my chemical equation up here. So what we end up doing is a little bit of very, very easy stoichiometry. And this is maybe a jump that you guys have already made, but my moles of hydrobromic acid are equal to my moles of hydronium. And this is because I have a 1-to-1 ratio in my balanced chemical equation. Now, you don't necessarily have to write the stoichiometric step out, but I want to show you where it comes from, and just instead of just saying, okay, yeah, they're equal, like, okay, well, why are they equal? How do you know that? Well, you can actually do the stoichiometry. Okay, so it is the same number of moles. Again, because my balanced chemical equation, this is a 1-to-1 ratio, which is always our favorite stoichiometric ratio. And so this is also our moles of hydronium. So at this point, again, I'm kind of moving forward with the grams converting to moles, but I've also kind of been moving backwards from like, I need this. So now I can kind of put these two pieces together because I have my moles of my hydronium, which I know can go right here. So let's go ahead and plug that in. So again, I'm trying to get to my concentration so that I can plug in for my pH. So I've got this value, it's right here, 0.4325. This is moles of hydronium. Okay, so now I need liters of solution. So I haven't dealt with volume at all. What's going on with this liters of solution? Let's go back to our problem and see if we can get some help here. Okay, so we have 35 grams of HBr. Okay, we've already done this. Is added to, okay, so here is our volume, 975 milliliters, again, of solution. So this is going to be the piece that we are going to need for this liters of solution. But there is a very small wrinkle. I'll do this in green. We have 975 milliliters, but this formula calls for liters. So again, just a really simple calculation to convert from milliliters to liters. This is something that you're probably not necessarily having to write down because all you need to do is move the decimal. And now I have this in liters. So this is liters of solution. So now I can plug that in to my concentration, 9750 liters of solution. So now I can actually get a concentration for my hydronium ion. And I have that number. Where do I have that number? Here I have that number. So 0.4437. Again, this is molarity, and this is for hydronium. Okay, so like fantastic, great, we've got a concentration. What do we do with that again? Well, we're going to take this concentration. We're just going to pop it straight into pH, and then there's our pH. We have calculated our pH once we get to that step. I'm going to have to squeeze this in here. So I'm just going to rewrite my equation here. I'm plugging in my concentration here. Make sure, of course, when you're first doing these problems that you find the log button on your calculator. All right, so we get a pH of 0.353. We'll put that in a box so that it makes it clear that I have calculated the answer and it is way down here. Now, before I leave this problem, I do want to ask myself, does this make sense? Does it make sense that I have a really, really low pH, a very small pH? Well, yes, it makes sense. I have an acid in solution. So for sure my pH should be less than 7. I've got 35 grams, or, I've got almost half a mole here. So I have a pretty good amount of a strong acid in solution. So yes, my pH should be very low, which tells me that this is a pretty reasonable answer, even if maybe I'm not sure about the number. So it's always nice to do those kind of logic checks, especially if you're working on a test and you can say at least, does this answer make sense? Am I in the ballpark? And yes, this answer makes sense. I'm certainly in the ballpark. Okay. All right, doesn't look like there are any more questions right now. So let's go on to this problem. Okay, so let's just read it. If a student needs to make 500 milliliters of a solution with a pH of 11.5, how many grams of potassium hydroxide should she use? All right, so we've got the same kind of problem, but it's a little bit different. So we have potassium hydroxide. This is a base. All right, but I'm still trying to find pH, which means I'm still going to be looking at trying to get to this equation right here. But I have a little bit of a problem that I can see, as this is, of course, concentration of hydronium, which we were able to calculate last time, but I don't think I'm going to be able to get to concentration of hydronium for this problem. But again, if you're unsure, let's just go ahead and, if you're unsure how many steps, so like I kind of start at the back end of the problem and work forward, and then I'll start at the top end of the problem and work forward, and then I try to meet in the middle. So what I'm going to do first is I'm just going to write my chemical equation. So I've got potassium hydroxide. That's going to give me the potassium cation and the hydroxide anion. Okay, that's fine. That's well and good. I know it's a base. I know it's supposed to give me hydroxide. But I'm still having a little bit of trouble because I could get the concentration of hydroxide, but I need the concentration of hydronium. So I'm seeing a mismatch here, which makes me go, okay, is there another way around this? Well, there are actually a couple ways around this, but what I tend to see first is, what if I were to calculate pOH? Because then I need concentration of hydroxide, and I have hydroxide in my chemical equation, which means I can calculate that concentration because I know how much I have. So I am going to focus on calculating concentration of hydroxide at this point as I kind of move forward. And then I think I'm just going to calculate pOH first. And again, I'll show you how to kind of bring all of this together. All right. So we've got hydroxide. We know we need concentration here. We've got a volume. Okay, that's great. So a volume is going to be part of our concentration. So again, remember, molarity equals moles of solute over liters of solution. So I know I can put a liters of solution here, but now I'm running into another problem, right? I need liters of solution and moles of solute to calculate my concentration. Well, do I know my I certainly don't know my moles, but do I know my grams? No, I don't know my grams. Again, this is my volume of solution, so this goes in my denominator. So I'm having trouble here, like what do I do? So now you might get stuck again. This is why I really like this problem, because I feel like it puts up these common roadblocks. Okay, so you go back and you look at what you have and what you can use. So this 500 milliliters is going to go here, but I don't have anything else to plug into this. So let me go to the other piece of information that my problem gives me. A pH of 11.5. Okay, well, let's see if I can use that to help me, again, connect kind of the start of my problem and the finish of my problem and see if I can make sense of what's going on here. Well, if I have a pH of 11.5, all right, that makes sense. It's a high pH. This is a base. What if I converted this to pOH? So here is an equation I can use to convert pH into pOH, or calculate pOH. So let's go ahead and do that. And this is where I think it's valuable, just in terms of problem solving skills, is to try a way first. And if you hit a roadblock, back up and try another way. So it's nice to stay flexible and not always think, okay, these problems have to be step 1, 2, 3, 4, 5. It can help to have a framework, but always remember to be flexible within your framework. So I've got a pH of 11.5. What is my pOH? All right, so I'm just going to rewrite my equation down here. plus POH. And let's put in our value for pH. Again, it's just coming straight from the problem. So now my value for POH is equal to 2.5. All right, that's great. So now I have my POH. So if I go back again to kind of my bank of equations here, what if I were to plug POH in here? I could get concentration. Well, maybe this concentration problem here is less about moles and liters, but finding concentration in liters. Okay, so again, I'm kind of trying new things. If I need to take a step back, I take a step back. If I can take a step forward, I take a step forward. Again, some of this is a little bit guess and test, especially if you haven't seen these types of problems before. And you just kind of try a method and see how far it takes you, see what information you can get from it. The main thing I say on this, especially if you're taking a test, is when you read a problem, I really think always your first step should be don't panic. You can do more than you think you can do, but just take a deep breath. Maybe just take one small step on the problem. Okay, but that's like test taking skills. We need to finish this problem because I have a whole neutralization to get through too. Okay, so I guess I'll do it up here. I'm just going to rewrite my equation for POH and concentration of hydroxide. Now I'm going to put in what I know. So I know my POH is 2.5. So I can calculate my concentration of hydroxide. Why did I write that? I wrote 10 because I was thinking of doing the anti-log there. I still wrote 10 again. I can't get anti-log out of my head. This is concentration of hydroxide. Okay, and this equals 3.16 times 10 to the negative third. Again, that is molarity, that is concentration. I just couldn't stop doing the anti-log. So again, when you're doing these in terms of putting it in your calculator, when you're trying to solve for concentration, it is 10 raised to the negative 2.5. And that's where you get your 3.16 times 10 to the negative third. So again, make sure you find all those buttons on your calculator, especially if this is your first time through acids and bases and calculating logs and calculating anti-logs. Okay, so I've got my concentration of hydroxide. I'm going to pop back again to my molarity equation here because now I can fill in more variables. So I have my concentration. I have my liters of solution. So I can calculate my moles of solute. So again, this is a problem that maybe you first approach like the previous problem we did where you're trying to get to moles of solute first. And again, you find roadblocks like I can't do that, I can't do that. Well, what can you do? So hopefully at this point, even if you were unsure that you wanted to solve for moles of solute in that first couple of steps, you've gotten to the point now where you think, oh, well, I can solve for moles of solute, and I think that's going to help me. Okay, so we've got our concentration. Let's go ahead and get our concentration in. So now I've got a little bit of a longer calculation. And what I'm going to do for this one, just because in the last one I used the formula, I'm going to show you how you can also use concentration more as a conversion factor or as part of a dimensional analysis problem. So this is, moles of hydroxide, and this is liters of solution. And of course, we always put it over 1 liter of solution. So this is true for grams per mole. It's grams per 1 mole. If you have a 22.4 liters per mole, that's per 1 mole. So this is 3.16 times 10 to the negative third moles of hydroxide per 1 liter of solution. All right, I know my liters of solution. Well, I almost know my meters of solution. I just need to do a little conversion there. So if I have 500 milliliters, again, this is just a really simple conversion. You're just going to divide by 1,000. Of course, 0.05 liters. Again, a lot of times when you get used to this, you just start moving the decimal instead of writing this out. But just in case anybody out there needs it written out. So if I multiply by my 5 liters of solution, notice what happens here with my units. This cancels, and now I'm left with moles of hydroxide. Okay, well that's fantastic, right? Moles of hydroxide, I'm super close because here I've got hydroxide right here. I just need to get back to potassium hydroxide. So how do I switch from talking about hydroxide to potassium hydroxide? You just use stoichiometry. And again, this is really easy stoichiometry because this is all a 1-to-1 ratio. So 1 mole of hydroxide is the same as 1 mole of potassium hydroxide. This is something that you will probably end up skipping as you get better at these problems. So now my moles of hydroxide have canceled. I've converted to moles of potassium hydroxide. So now I'm really, really, really close. But I need grams of potassium hydroxide. So I need 1 more factor in this dimensional analysis problem, or you can think of 1 more conversion factor in this conversion factor problem. This is why having those dimensional analysis skills, I think, is so important because they really transfer over to a lot of other things like stoichiometry, like acids and bases. Okay, and just to show my moles of potassium hydroxide have canceled. So now I have calculated grams of potassium hydroxide. That's exactly what the problem wanted me to calculate. So all I have to do now is put this in my calculator, which I have done. I have that answer. Where is it? Here it is. 0.886 grams of potassium hydroxide. All right, and this is my answer. So that is how many grams that the student should add to 500 milliliters of solution to make a solution with a pH of 11.5. This is actually something that if you're someone who preps labs, you do this actually all the time. So this is a very practical type of calculation to do if you're doing any kind of lab work. It's really, really common. Okay, question. Oh, so sorry, I've got some question. Oh, organic chemistry question. Okay, so Joe, this is actually just a Gen Chem session. But it's possible that OG benchmarks, organic chemistry is his expertise. He might be able to help you with that. Oh yeah, conjugated dienes form resin. Okay, so Joe, what I would suggest at this point is go and check out the other videos on ChemHelp ASAP. So usually the videos with the white thumbnails are going to be your organic videos. And I believe there are some videos on dienes on there. So we're hoping to start an organic chemistry live stream as well, but it's just we just don't have it. It's not possible in the schedule right now. But fingers crossed, we'll be able to do it in the fall because obviously, yes, we know there are plenty of organic questions out there as well, and it would be cool to have a Gen Chem live stream and then also have Erland do an organic live stream as well. So yeah, but yeah, go check out the videos. Oh, it looks like OG Benchmarks is going to go pull up a video for you anyway, so hopefully that'll help. Okay, so sorry, furry therapist, you had a different question I missed off topic. But have you done a segment over equilibrium? Yes. Okay. So, equilibrium. So that was actually something that I was thinking about doing for next week is doing specifically acid and base equilibrium. Now, equilibrium covers a lot of different things because you can have equilibrium of like gases. You can have, like solubility equilibrium too. But because I kind of started acids and bases, I was thinking of actually about doing weak acids and bases and doing equilibrium problems, not only just weak acids and weak bases alone in aqueous solution, but what happens when you react like a weak acid with a strong base, and how do you do those kind of calculations? So that is my plan for next week. But yes, I do have videos on that. I did live streams on acids and bases a couple of months ago, and now I can't remember how long ago, but if you go and look under the live stream playlist, you will see other acids and bases, and then it's just depending on how many questions I get through. But this is something that I want to go through again because it tends to come up every semester is not only acids and bases, but equilibrium and weak acids and bases. And fingers crossed, I get to at least the definitions of what's the difference between a strong acid and a weak acid and a strong base and a weak base. But yeah, I'll do that. Oh, the schedule lines up with the equilibrium test. Okay, so then for you, for a therapist, I do recommend going back and looking through all of the live streams that I've done, because I have done those equilibrium problems before. You'll just have to look back. I mean, I've got them all there. I want to say like I did it maybe in November or something, but it should be fairly obvious where it's there. And I know OG Benchmarks is hopefully looking for some video links to pass on too. But if you put a comment in like this live stream and just remind me, then I'll try to go back and find the other live streams that I've done where I work through some of those equilibrium problems, because oh my goodness, it just takes so much time and so much space to do those calculations. But when you're done with them, I just find them really, really satisfying. But I do have other stuff on here for equilibrium, because those can be bears for sure. Okay, I think I got all of the questions right now. So let's go ahead and go to our titration problem. So finally, our titration problem. Now this is a simple titration problem because I'm going to have a strong acid and a strong base. Let me actually read the question first, and then we'll talk about it. Okay, so a 15 milliliter sample of 0.950 molar hydrochloric acid is titrated with 0.75 molar lithium hydroxide. How many milliliters of lithium hydroxide are needed to reach the equivalence point? What is the pH at the equivalence point? And then what is the pH when 5 milliliters of lithium hydroxide have been added? And then we do the same thing, the pH at 15 milliliters, then the pH at 20 milliliters, and the pH at 25 milliliters. So this is kind of a classic titration problem, and you calculate pH at different points along the titration curve. And I hope we can get through it. Oh, so we've got some more questions. How do you find the pH of an acid in a double displacement reaction? Okay, so for a double displacement, so you're talking about an acid and a base that, okay, so I'm just going to write a little bit here. So I think you're talking about like maybe sulfuric acid and sodium hydroxide, because you need 2 moles of hydroxide for every 1 mole of sulfuric acid. So this would give you sodium sulfate and water. Again, I'm just answering a question. This is not this question right here. You're going to get 2 moles of water, and you're going to need 2 here. So the first thing is to make sure you have a balanced chemical equation. And then if I'm just going to swipe back here. So if you see, I am doing stoichiometry in these problems, but most people skip this step because it's 1-to-1, so it doesn't actually change your math. But if you remember to put your stoichiometry in here and you're using your balanced chemical equation here, then you will end up putting that 1-to-2 ratio in the proper way, depending on what the question is and which way you're going. So sometimes you might be multiplying by 2, and sometimes you might be dividing by 2, again, just depending on how your units are working out. But I would definitely start with whatever your balanced chemical equation is. Well, write the chemical equation and then balance it. And then when you're doing your calculations, make sure you're putting your stoichiometry in. And even for this one right here, which is going to be a 1-to-1 equation because I made it easy, I will still show how the stoichiometry works. So working through this one might at least give you some idea of how to handle these 1-to-2 ratios. So, like sulfuric acid is a diprotic acid, but you might have a triprotic acid. You might have something like phosphoric acid, and then you've got a 1-to-3 ratio. Or you could have a base like calcium hydroxide has 2 hydroxides, and you're reacting that with hydrochloric acid. But it's all about keeping track of the stoichiometry in your calculations. But again, going through this one, I think will help because I will also still show what the stoichiometry is. It's just going to be easy math-wise because it's going to be 1-to-1. Okay. All right. So I think we're good. Oh, good. So OG Benchmarks is talking some organic chemistry in the chat, which is totally fine. All right. I'm going to erase this equation because this is not the balanced chemical equation for this question, but I really appreciate the questions. Feel free to ask anything you want, and I will try to answer as best I can. So I also try to have examples that I think will fit, but if we really need to go off topic, I'm fine with that. We can totally go off topic. I just won't have the calculations done. I'll just have to grab my calculator for it. Okay, so, all right. Oh, go OG Benchmarks. I'm glad he's talking about rotating pi bonds. I like my math. I really like my math. Okay, so let's start with our acid base. And again, let's start with our balanced chemical equation because, as always, you have to deal with stoichiometry, but this one is really easy. I purposely chose this one because it was a 1-to-1 ratio. So we're going to make lithium chloride and water. And just as an aside here, for any neutralization reaction, which is what you're doing in an acid-base titration, you're doing a neutralization reaction, these are going to form salt and a water always. So you could also think about this as a double displacement reaction. You're just you can think about either flip-flopping cations or flip-flopping anions. And some people actually, instead of writing H2O for water, when they're thinking about double displacement, they'll write HOH. It's the same thing. We just usually write water as H2O instead of HOH, but you have a proton H and hydroxide OH that come together to form water. Okay, so that's just a little bit of a rabbit trail there. Okay, so we've got our neutralization reaction. This is a 1-to-1 ratio. Again, I wanted to choose an easy one at least to start with before we jumped into like a 1-to-2 or a 1-to-3. You could do that as well. Let's talk about the equivalence point. All right, so the equivalence point. So what happens at the equivalence point? What is true at the equivalence point? And we've got, so at equivalence, what happens is we have our moles of our hydrochloric acid equal our moles of lithium hydroxide. You can also think of this a little bit differently. So if you think about doing this in the lab as an actual titration, so for this problem, we have started with a 15 milliliter sample of acid. The equivalence point occurs when you've added just enough base to completely neutralize the acid. So for our situation right here, because we have a 1-to-1 ratio, these moles are going to be equal. But this is why you want to make sure you balance your chemical equation, because if you have a 1-to-2 stoichiometric ratio, then these moles are not going to be equal. You're going to have maybe 1 equivalent mole of acid and 2 equivalent moles of base, or vice versa. Maybe you need 2 equivalent moles of acid and 1 equivalent mole of base. This is why anytime I'm doing a chemistry question, I always want to write down my chemical equation and make sure it's balanced first, because that is going to give me a lot more information than I think students realize at first. But that balanced chemical equation is super important. Okay, so it looks like, hold on, some more questions. Think about pi bias back and pH. Yeah. No, I agree. Okay. Love and hate titration labs. Yeah. So, yeah, it's so satisfying when you're doing a titration lab, especially if you're using phenolphthalein as an indicator and you're going for an endpoint and you get that really nice light pink color. Like, nothing is more satisfying. But even as we do this calculation, you'll see you only have to go over by the tiniest little amount, and suddenly you've got that really hot pink solution. You've totally overshot the endpoint, which means you get to repeat that titration again. So yeah, titrations can be a little bit of a love-hate reaction. The other thing I'll say, just talking about titrations, remember that equivalence point is not necessarily the same thing as end point. So your equivalence point is mathematically or stoichiometrically, again, for this equation here is when my moles of hydrochloric acid are equal to my moles of lithium hydroxide. Your end point is when your indicator changes color. Like for phenolphthalein, you're usually going from colorless to pink. I mean, you can go the other way, but usually you're going from colorless to pink. That is your end point. We consider it close enough to the equivalence point that we can do calculations from it, but they are not actually the same thing. So this is why we use different words for it. So your end point is when your indicator changes color, and your equivalence point is what you calculate from your stoichiometry. That's when, for this equation, your moles are going to be equal to each other. So just FYI. Okay, is there an approximation? Is there an approximation you can do for the end point? Because we will calculate where the equivalence point is for this problem here. You can always calculate where your equivalence point is. You just have to know basically how much you have of your sample you're starting with, and then how much you're adding into it. But yeah, for your Oh, for logs and their inverses, like yes, you can absolutely do approximation for logs and inverses. So one thing that I also do is I teach an MCAT class, review class for Princeton Review, and you're not allowed to have a calculator on your MCAT class, but you still have to do acid base work. So you have to do approximations without a calculator. So if you remember your pH and your pOH scales, they are inverse logs. So if you have a pH of 1, your concentration of hydronium is 10 to the negative 1. If you have a concentration of 8, your concentration is 10 to the negative 8. So they keep it really simple so that you really only have to take a look at the exponent. But yeah, you can absolutely do approximations in your head just based on the rules of logarithms. Approximating logs, yeah, approximating logs are, yeah, just you have to get used to it. But that's all right. You get used to it, you practice it, and it does help you understand how the pH and the pOH scales actually work. Okay, so I am actually want to do some of these problems. So, okay, so at the equivalence point, our moles of HCl equal our moles of lithium hydroxide. So we can actually calculate how much, and this is what they want to know, how many milliliters of lithium hydroxide are needed to reach the equivalence point. Then we'll worry about what's going on with acids and bases and the pH and all that good stuff. So the first thing that I want to know is how much hydrochloric acid I actually have in my sample that is to be titrated. Of course, this is given to me in a concentration with a volume, so I'm going back to molarity equals moles over liters here. So I have my concentration 0.950, that's molarity. I don't know yet my moles. This is, moles of hydrochloric acid. But I know my liters of solution, so I have 15 milliliters of solution, which means I have 0.015 liters, which means my moles of hydrochloric acid equal 0.01425. Again, that's moles of HCl. So that is how many moles of hydrochloric acid I have in probably my Erlenmeyer flask, because I'm doing this titration, right? Okay, so again, at the equivalence point, I need to have this many moles also of my base, of my lithium hydroxide. So this is going to be equal to, again, the same number of moles of lithium hydroxide, and I'll write up here, this is at equivalence. Okay, great. So I know how many moles I need at the equivalence point. The problem asked me for milliliters. I'm going back to my concentration equation here. So molarity equals moles over liters. I do have my concentration of lithium hydroxide. That is right here. So that is 0.750. I know my moles. I just calculated that. Again, this is why one-to-one is so easy, but this is just stoichiometry. This is just because of the one-to-one ratio right here. That's all it is. Lithium hydroxide, and then I'm just going to have X liters of solution, because that's what I'm solving for. I don't know what it is yet. So after I do a little bit of algebra here, I can get X equals 0.019 liters of lithium hydroxide need to be added. This is the same thing as, of course, 19 milliliters of lithium hydroxide. So my equivalence point occurs when I have added 19 milliliters of lithium hydroxide. So this is when, again, I have the same number of moles of hydrochloric acid equals the same number of moles of lithium hydroxide, because this is a 1-to-1 ratio. Okay, now let's deal with what is the pH at the equivalence point. So it's pretty easy when you have a strong acid and a strong base. You would probably already guess this. You'd say the pH is 7, and you would be right. The pH is 7. pH equals 7 at the equivalence point. But why does the pH equal 7 at the equivalence point? Okay, so if we think about, again, going back to our balanced chemical equation, we don't have any more hydrochloric acid. We don't have any more lithium hydroxide. Those have all been used up. So what do we have left in solution? Well, we have a salt and we have water. And specifically, we have a salt here that has no acid-base properties. Oh, that's another thing that we could do a live stream on is acid-base properties of salts, and how do you calculate pH if you've got a salt with acid-base properties. But again, we'll do that later. So what dominates your pH? Well, your water dominates your pH. That is what is most important at the equivalence point of a strong acid and a strong base, is your autoionization of water, which means you put two water molecules together and you're going to get hydronium and you're going to get hydroxide. So then what is the concentration of, say, your hydronium here? Well, it is 10 to the negative 7th. This is your concentration of hydronium. Oh, this comes back to your question, Joe, about using not necessarily using your calculator to find the pH here. So the pH is 7 because this is 10 to the negative 7th. So your concentration of hydronium in this case, well, it's not pure water, it's water and a salt that has no acid-base properties, and that is key. Then your pH is equal to 7 because you're going to take the inverse log of this. Sorry, I should write this. Okay, so pH equals negative log of hydronium and negative log of, we can call it 1 times 10 to the negative 7th. Maybe that's a little bit easier for people. And then your pH is equal to 7. So in terms of those cases, like, it is really easy to just mentally work through the what is the pH of that without having to grab your calculator. Although you can always grab your calculator if you want to. If you're not taking the MCAT, don't worry about it. Just go ahead and grab your calculator. I promise it will give you the right answer. So this is what is going on at the equivalence point, and this is going to be true at every equivalence point of a strong acid reacting with a strong base. At the equivalence point, you're going to have no more strong acid, you're going to have no more strong base, and all you're left with is water that has some acid-base properties. So that is going to be a pH of 7. Now, it's totally different if you've got a weak acid reacting with a strong base or a strong acid reacting with a weak base. Then at the equivalence point, your pH is not going to be 7. You have to actually calculate what your pH is going to be. Okay, so yeah, I think we're good with this. Okay, all right, good. And we're going to need to keep some of these numbers. All right, so we're definitely going to need to know our moles of, sorry, not our moles of lithium hydroxide. I meant to box our moles of hydrochloric acid because we're going to need to use this as we titrate this acid. So we're going to be adding in a certain amount of lithium hydroxide, and we need to figure out what is left over and then how much of that is left over. Because you can see if our equivalence point here is at 19 milliliters, we've got a couple of calculations at 5 and 15 where we haven't reached the equivalence point, so the acid dominates. And then at 20 and 25, we're past the equivalence point, which means the base is going to dominate and we're going to have no more acid left. There's no way I'm getting through all these calculations. It's just not going to happen. It's okay. Get through as much as we can. All right, so I'm going to still keep our balanced chemical equation at the top of the screen so that I can, no, I don't want to do water first, so I can reference that plus H2O. Let's make that I a little bit better. All right, so let's just go ahead and do the calculation when 5 milliliters of lithium hydroxide has been added. So how do we do this? What does this look like? What are we going to do? Okay, so if 5 milliliters of lithium hydroxide has been added, I want to know how many moles that is. Because again, I'm going to be doing stoichiometry. I think a lot of students feel like acid and base is not the same as stoichiometry, but yes, it's the same as stoichiometry. You're just using an acid and a base instead of like a salt and a salt to make a precipitate, you know. So it's the same thing. We're really just doing stoichiometry. We're just doing it with acids and bases. So let's go ahead and figure out how many moles of lithium hydroxide I have added at this point. So moles of lithium hydroxide over 1 liter. That's really bad. It looks like I wrote mule. Okay, so mole lithium hydroxide. Again, this is my concentration. My 0.75 is my concentration of lithium hydroxide. I have added 5 milliliters or 0.005 liters. Again, I'm just kind of skipping over dividing by 1,000 to change milliliters into liters. So I have added 0.00375 moles of lithium hydroxide at this point. Okay, so this is where I do my stoichiometry. 1 mole of lithium hydroxide per 1 mole of HCl. And so I have used this many moles of hydrochloric acid. Again, if you didn't have a 1-to-1 ratio here, if you had a 1-to-2 ratio, you want to make sure that you're using the right numbers in the right place for your stoichiometry. Again, this is a 1-to-1 ratio, so this doesn't change my math. So when I have added this 0.00375 moles of lithium hydroxide, of course it reacts with the acid instantaneously. We consider it instantaneously. If you've done these titrations, you know it reacts right away. So I have now used 0.00375 moles of hydrochloric acid. What do I have left over? So do I have more base left over in the flask, or do I have more acid left over? Well, at this point, I'm before the equivalence point, I haven't used up all my acid. So my lithium hydroxide is my limiting reagent. I have excess hydrochloric acid. Sorry, I said lithium. Lithium hydroxide is used up. I have excess hydrochloric acid. I want to know how much excess hydrochloric acid I have, because that is going to drive my pH. My acid is driving my pH. Okay, so how much hydrochloric acid is left after I've added this 5 milliliters of lithium hydroxide? Okay, well, let's go hydrochloric acid. How much hydrochloric acid did I start with? Well, I did that calculation back here. Blurp, blurp, blurp. Here it is. I boxed it right there. So I started with 0.01425 moles. That's how much hydrochloric acid I started with. This is how much I've used. So I have used 0.00375 moles. So how much is left over? I'm going to subtract these two. So this is what remains. I have 0.0105 moles. Again, this is HCl is remaining. So this is how much hydrochloric acid I still have in solution after neutralizing it with 5 milliliters of lithium hydroxide. Okay, so now I'm still after pH, but now all I have to deal with is what is the pH if I have a solution with this many moles of hydrochloric acid. Well, this is a problem that's just like the almost just like the very first problem we did, where you just have an acid in solution. We've already taken care of the neutralization part. We've taken care of the stoichiometry part. Now we're just simply calculating the pH of an acid in solution. So this part hopefully in your mind becomes a little simpler because you're not taking care of that neutralization anymore. All right, so the thing that I do want to point out, again, this still goes back to stoichiometry. It's just such an important part of chemistry. When you have hydrochloric acid in water, of course, you are making hydronium, and that is what you're measuring with your concentrations. You want your concentration of hydronium or H+. But again, notice what is your mole ratio here. Your mole ratio is 1-to-1. This means that my concentration of hydrochloric acid is equal to my concentration of hydronium ion, which makes, again, the math a lot simpler, because I know if I just calculate my concentration of hydrochloric acid, that is my concentration of hydronium ion. However, if this was like a 1-to-2 ratio, again, you'd have to put that stoichiometric step in to make sure you account for, again, if you've got a diprotic acid or something going on like that. Okay, so I have my moles of hydrochloric acid. Remember, molarity equals moles over liter for liters of solution. So let's plug in what we know. We know our moles. It's right here, 0.0105 moles of HCl. Now we need to put this over our liters of solution. This is a little bit tricky, so just be aware. So what I need to do is I need to make sure that I'm adding my volumes. So I started with a 15 milliliter sample of my acid, and at this point I've added 5 more milliliters because I added 5 milliliters of my lithium hydroxide. And then of course you need to divide this by 1,000. so that you convert it into liters. So maybe I should make my parentheses a little bit bigger here. So in other words, let me just write it like this, so hopefully it's a little bit more clear. Moles of HCl over 0.0, that's 20 milliliters, 0.0 liters. Okay, so this is what I'm doing, and this is a part that a lot of students miss, is when you're doing your liters of solution, it's liters of the whole solution, or you can think about how many liters do you have in that Erlenmeyer flask that you're titrating in. Make sure you add the volume you started with plus how much you have added. In this case, we've added 5 milliliters of lithium hydroxide. Okay, so we have, let's do this calculation. Where is that? 0.525. This is my concentration of HCl, which is also my concentration of hydronium, because remember they are equal. 0.525 molar. So I can calculate my pH. It's just negative log of 525. And so my pH is 0.280. Okay, so this is my pH after 5 milliliters of base has been added. Does this make sense? Yes, this makes sense because I have my strong acid in excess. So I should, of course, have a pH that's less than 7. But again, because hydrochloric acid is a strong acid, it is not unusual to have a pH that is very, very low, even with, only 0.015 moles of acid in solution. This is kind of the beauty of a strong acid. Oh my goodness, it's already after 8 o'clock. Okay, so we're done. As usual, I don't get through all of my problems. But yes, definitely let me know. It sounds like doing weak acids and weak bases and playing around with equilibrium and maybe doing a titration with like a weak acid and a strong base or something similar is the thing to do. Also, maybe doing a titration that is not a 1-to-1 ratio, but like a 1-to-2 ratio as well. So I will continue doing acids and bases next week. Feel free to ask any questions. And yeah, as always, just let me know what you want to see, what kind of problems you want worked. I'm happy to work any Gen Chem problems, but at least right now I'm focusing on acids and bases. So thanks so much for joining, and I hope to see you guys next week. Bye.